In the next couple of pages of notes, what I want to do is go through and compare how do we relate some of the more fundamental Maxwell's equations with measurements that you would take on in the laboratory or across, say, a standard solenoid that we use in actuators, motors. So if you think about this solenoid, we're running a current through it. Here it goes through this loop, and as you know from undergrad physics, if we take the right-hand rule, we generate a magnetic field within this loop. And the way that this is related to one of Maxwell's equations, this one in particular, is, so if you have current density running through this wire, it's related to the curl of the magnetic field. And the key thing to note here is we can use Stokes Theorem. So we can integrate this over a cross-section area of this loop. This is my unit tangent vector, so that tangent's moving along the direction of the wire. And so if you integrate over that contour, you get the current. So this is often used to determine like how many loops you need to generate a certain magnetic field. The other important thing is flux measurements. And from the fact that we have a divergent free B field, this must contain closed lines. So, of course, it's divergentless. So if you were to look at these flux lines going through here, these all have closed lines. These are moving out, but if I was to draw it out further, you would see that those are all going to be closed lines. There's many cases where we can estimate an average B field if you have a long solenoid, and you can neglect these end effects. And so when we can make that approximation, we can take the B field, dot it with the normal over this area, for example, so in here, and we get a flux across this area in units of Weber. And we can write that in terms of this average flux by this potential. So we often will compare that with our magnetic field. And so you can make the connection here with the number of loops in, so you get the strength of that magnetic field. So instead of taking the area, this is moving along that contour instead of the cross-section area. So say if it's a linear magnet, so we take that method we used before where we have a linear relation between the magnetic field and magnetization. So we have this constitutive law. We say that it's an average uniform field, tangent vector. We substitute those relations in, and if we can say that this is uniform, meaning there's no charge leakage, in the end what we get is a useful relation known as reluctance. And so we can take this reluctance and relate it to the current, the number of coils in a loop, and the geometry and permeability of our magnet. I'm sorry, of our material.